Action. Oh, we're going straight away. Right. Question 3. The following algorithm displays 3 values for each positive integer input. There's the whole thing. I'm not going to read that. Very dull. Apply the algorithm to the input n equals 5. You only need to write down values when they change. You should record the line numbers, but there is no need to record passing through lines 20 and 60. Okay, so let's go. We begin with line 10. Input a positive integer n. The question says n is 5, so let's input 5. Then it said, if n is an odd number, jump to line 80. It is. So we're going to jump to line 80. That's going to be the next thing we're going to write. Let p equal 0 and m equal n. So I think that's where we're up to, isn't it? Then line 90 follows that. And line 90 says, let a equal m squared plus 1 times 2 to the p minus 1. Ooh, that's exciting. So m squared plus 1, that's 26 times 2 to the p minus 1. That's 2 to the half. That is a half. 2 to the minus 1. So that's 13. So we put that in there. See how well this is going. Line 100 comes next. Let b equal a minus 2 to the power of p. So b equals a, 13, minus 2 to the 0. 13, take away 1, would be 12. And then it says, display n, b, and a. That's some basketball thing, isn't it? And then stop. So n, b, a. There we go. Right. Great. A nice little bit of 4 marks for that. Then we have to do the whole thing again with the input of n equals 20. Notice how that's all that you needed. So it did say you didn't need to fill in all the other values. A few people did put in lots of other numbers kind of in this space here. But it's alright, you don't need to keep recording those. It's okay to do that. But what does matter is that this line structure is quite rigid. So you can't kind of blur lines together and do lots of things at once. Shh, Jack. Right. Part 2. We're supposed to apply the algorithm. I need to look at my copy of the algorithm now. With n equals 20. So input a positive integer. Then it says, if n is an odd number, jump to line 80, but it's not. We're on line 30, or line the way.
No, I kicked it by accident.
Oh, no. Awful. Right, so what did we say? Let p equal 1. We're on line 30 with p equals 1. Then it says, let m equal n. So that's just line 40, m equals n.
We have a question.
Then divide the value of m by 2 and make this the new value of m. So line 50, divide that by 2 and make that the new value of m. Line 60, if m is an odd number, jump to line 90. It's not an odd number. So line 70 says increase p by 1 and go back to line 50. So line 70, we're going to increase p by 1. And we're going to go back to line 50. Line 50 said divide the value of m by 2 and make this the new value of m. So that we're back to line 50, dividing that by 2 and making that the new value of m. Line 60, if m is odd, jump to line 90. It is odd, so we're going to jump to line 90. Line 90 was the one that said let a equal m squared plus 1 times 2 to the p minus 1. So m squared plus 1, that's 25 plus 1 is 26, times 2 to the power of 1 this time. 26 times 2 is 52. So we've got a 52 appearing there. After line 90 comes line 100. Line 100 says let b equal a minus 2 to the p. So a, 52, minus 2 to the power of 2. 52 minus 4 is 48. Line 110, display n, b, and a, and then stop. So n is 20, b is 48, a is 52, and then stop. Great, we've had a lot of fun. Right, explain what happens when n equals 2 to the x for some positive integer x. Okay, so we've got to think through what would happen if n is 2 to the power of x. Well, right, what would happen? 2 to the x would be an even number, wouldn't it? So that would be the start point, because that must be. So we would start by letting p equal 1, and then we'd let m equal n. So that would, then we'd divide it by 2. And we would keep on dividing by 2, because that's the little loop that we were in here. We kept on dividing it by 2 until it was no longer an even number. Now, if it's a power of 2, if we keep on doing that, eventually the only way that we could get to it not being an even number is it would end up being 1. So that's the first thing to notice with this. 2 to the x will be halved repeatedly until, that's not how you spell until, doesn't matter, until m equals 1. That's where we get to. Right. And as we do that, well, we're recording how many times we're doing that, are we? Yeah, as we do that, p is reducing by 1. And somebody just kicked the thing. Oh,
it wasn't me.
Oh, it was Mitch this time. He then swore, but I don't think it was audible.
You're not in the thing now.
I'm not on the thing.
You need to go that way. Yeah, no, you're alright now.
Oh, great.
Yeah.
I've always been alright. Right, so we're going to keep on doing that. So p is going to keep on increasing, won't it? And p will end up being x. Because the number of times we've halved it is the number of powers of 2 that we would have. So, so then what would happen once we get to that point? So p is x and n equals 1. We're then in the bit where we let p equal 0. Which one is it? Oh no, at that point m is an odd number, so we're jumping to 90. So a is m squared plus 1 times 2 to the p minus 1. A would then be...
That's you.
What is that? So m squared plus 1, but we have now set m as being 1. So that is 2. M squared plus 1 times 2 to the power of p minus 1. And p would be x, so that's 2 to the power of x minus 1. Which is 2 to the 1 times 2 to the x minus 1. You add together the powers, so that is 2 to the x. B would be a minus 2 to the p, so that is 2 to the x minus 2 to the x. So b would end up being 0, and we would then display the values at the end. So the final values we display are n, which was 2 to the x, b, which ended up being 0, and a, which was also 2 to the x. And that would be our stop point. And so that's what we get to. They wanted, as part of your answer for that, you to demonstrate that you would keep on doing it until n became 1, iterate until it became 1. They wanted you to recognise that p would be x, and then they wanted to see the values of a as being 2 to the x, and b as being 0.